So in the last video I made on optimization, I shared with you guys my favorite framework that I used and continue to use for solving optimization problems in Calc 1 in the context of Calc 1. There were a lot of people talking about, well, what about this kind of optimization? I'm just focused on the scope of your calculus class. But anyway, I shared a framework and I wanted to do another problem using that framework to show you guys how it still applies. And also just to drill an extra practice problem with you all, because that is the best way to get good at these types of questions. And then what I'm going to do is show you guys how you could totally circumvent my YouTube channel and get the tutoring that you need just by using generative AI. This product, it's called MathGPTPro. I'll demo it later, but basically it's ChatGPT, but its user experience and its neural network is optimized for math problems. It's a tool that I really wish I had in school. I'll prove to you guys how it's pretty useful in this case. And it's backed by Y Combinator, which is a big credential. I feel like AI is very hot right now, and so there's a lot of products going around. It's this big contagion. And with that, a lot of products kind of scam you. But MathGPT is backed by YC. I've had several conversations with some of the co-founders, and they're really passionate about their product and doing the real thing. So I use it a lot, and I want to share it with you guys. But for right now, let's solve this the old-fashioned way, which is with your brain and a pencil. So it says the problem is that we want to maximize the area of a rectangle that's bounded by a horizontal line and a parabola. So if you kind of visualize this in your head, we'll draw a picture soon, but if you visualize it, you can kind of change the size of that rectangle and the area will change, but we want to find the dimensions that will maximize the area. And for that, we're going to use our framework. So the first step, if you remember, is to write down the goal of the problem, which in this case is we want to maximize the area of the rectangle. Step 2 is draw a picture, which I think is very important in this case because it's just a block of text, the problem is, and a picture really gets you thinking about what the next steps are. So let me draw that for you guys. So I'm going to do an XY coordinate system, and we have our line y equals 6, which is a horizontal line, and we have the parabola y equals x squared, which you know what that looks like, and then we have some rectangle which is bounded between this line and this curve. So you just want to draw a generic one, and we will assign our variables to this drawing, which is an important part of your picture. The picture is where you define these variables that you're going to use to set up an equation for the metric you're trying to optimize. Then you'll differentiate that equation once you have it in terms of one variable. So here's the rectangle, and the area is what we care about. So let me draw the rectangle off to the side here. Okay, here's the rectangle. What kind of variables do we want to use to set up an equation for the area of this rectangle? You might say, oh, length and width. But let's think about it for a little bit longer. What makes sense to use in this problem? Well, we're in the XY coordinate system, and we have parabolas and lines defined in terms of x and y coordinate points. So let's try to use x and y. How can we use that in this case? Well, if we think about what a generic x value would be, it would be some distance along the x-axis. And we could say that this point here is a really important part because this point, x comma y, is a corner of the rectangle. So if we call this x distance out from this corner of the triangle the variable x, then what is this side length of the rectangle? Side length would be 2x, right? So let me erase this L and W and we'll put in x, 2x actually. And then what is the height or the width or whatever you want to call it of the rectangle? Well, it's not y. You might think that it's just y. We have to think about it a little bit harder. Let's go back to the picture. What lengths do we know? Well, we know that the distance from the line all the way down to the x-axis is 6, because this line is at y equals 6. And we also know that this distance from the x-axis up into the bottom of the rectangle would just be y. So the width of the rectangle would be the difference between 6 and y, so 6 minus y. This is why a picture is so important, because you can draw those geometrical connections, and you can set up your equation. So let's do that. So let's set up our equation. So that's step 3. Step 3 is write a function for the variable you're trying to optimize, which in this case is area. So we'll say area of the rectangle is what? 2x times 6 minus y. But specifically, the third step is you want to get your area function, or whatever function, in terms of just one unknown variable, so that you can differentiate it. So we need to find y in terms of x. So pause the video, think about it a little bit. Okay, good. So you got it right. So y in terms of x is x squared, because we know that the y coordinate at this point is just whatever the x coordinate is after you plug it into your function for the curve, which is y equals x squared. So let's plug in this down here for our function for area, and we'll see what we get. So I've now written it as area as a function of x, which is really the end goal, just having it a function of one variable, is 2x times the quantity 6 minus x squared. So we distribute the 2x, and we get 12x minus 2x cubed. All right, so we're almost there. We're in the home stretch. We have a function for area. We want to optimize area. So we want to find the local maximum of this function. To do that, you take the first derivative, which in this case, thankfully, is pretty easy. It's just 12 minus 6x squared, if I did that right, using the power rule. And then we want to, so sorry, this is step 4. Step 4, find the critical points. I'm not doing a really good job outlining the framework, but I think you guys get the point. So to find the critical points, you set it equal to 0, the first derivative, and you solve for x. So in this case, what do we have? 6x squared equals 12. So x squared equals 2. So x equals plus or minus root 2. And it's at this point, when you find your critical points, that you need to check them to see if they're extraneous, if they even make sense in the context of this problem. So what is x? What are we saying x is? We're saying 2 times x is the dimension of this, one of the dimensions of this rectangle. So does it make sense to have a negative dimension of a rectangle? Of course not. So we're just going to say that x equals square root 2 is our only critical point. That at least makes sense in this context. So then step 5 is we want to see if it's local max or local min by using the second derivative test. You can do the first one if you want, but we're going to use the second because, I'll tell you exactly why. Because you want to use the second derivative test if it would be easy to compute the second derivative. In this case, our first derivative is just 12 minus 6x. So that's really straightforward application of the power rule to get the second derivative, so we're just going to do that. But if the first derivative was real hairy and it seems very formidable to get the second derivative, don't worry about it. Just do the first derivative test and plug in values to the left and right of your critical point and see if it corresponds to a peak or a valley. So for our second derivative test, we need a double prime of x, which is, up here we have a prime of x is 12 minus 6x squared. So a double prime would be negative 12x. And to do the second derivative test, you plug the critical point into the second derivative. So we want to calculate a double prime of root 2, which is negative 12 root 2, which don't worry about what it actually is. The main takeaway is that it's negative. So because it's negative, if you remember from the other video, negative is like a sad thing. So it's like a frowny face. And the mouth is a hump. So getting a negative value in your second derivative when you plug in a critical point corresponds to that, means that that critical point corresponds to a maximum because it's like the top of this hump. Which makes sense because we want to optimize area, we found our critical point, that's good. And it means it's a sign that we've been doing something right. So after you do the second derivative test, you want to do step 6, I guess, which is just like answer the question. So the question wasn't what's the x coordinate of the bottom right vertex of the rectangle when plotted in an xy coordinate plane. the question was, what's the maximum area? So we have to go back to our picture and plug in our values. So like if x equals root 2, which is the x that corresponds to a maximum area, we plug that in here and we get 2 root 2 for the length, and then 6 minus y is x squared, so 6 minus 2, so 4 for the width or the height. So let me make that more clear by drawing it. So here's that picture from above of the rectangle that we care about. So plugging in x equals root 2, we get 2 root 2 times 6 minus root 2 squared, which is 6 minus 2, which is 4. So our maximum area is nothing but 2 root 2 times 4, which is 8 root 2. Okay, pretty straightforward, right, to solve it by hand. Now let me show you why you don't even need my channel anymore, because you can use MathGPTPro. So let me jump over to the software and we'll type in the same question and see what it spits out. Alright, so we're in MathGPTPro. I've taken a screenshot of the word problem. I just pasted it as a picture in here, and I'll just say solve this problem using methods from Calc 1. Yeah, let's see. Area is given by length times width. This is really good. It starts from the basics. So use the same method that the width is 2x. Oh, the width is 2x. So it's expressed as 6 minus x squared. This is like what we did. And you can ask follow-up questions, which we'll do in a second. 6 minus x squared times 2x, which is perfect. And then it's like we need to find the critical points, which is the same exact language that we're familiar with. We do this by taking the derivative, setting it equal to 0. So we solve for x, we get x equals root 2. We also need to check the endpoints to make sure I didn't even do that. This is like catching me. This is really good. So then substituting them all in, it's like a of 0 is 0, a of root 2 is x root 2, and a of root 6 is 0. So like the maximum is obviously 8 root 2, and so that's the answer. That was clean. That was really, this thing like amazes me. And so you're probably wondering like, why is this better than just ChatGPT? ChatGPT is free. This is free to try, and you get a discount. You use the like referral link in the description. But it isn't free, but it's like what, $6 a month, which is like 1 cappuccino. Not even, these days. But you get a discount and everything. Try it out. Why is it better than ChatGPT? Because you can, like, the user interface is more helpful because it features like screenshot to ask. So I click that and I'll go up here and I'll be like, let's see. Y is, what about x equals negative root 2? I'll say that. So I'll screenshot this and I'll say, what about the solution x equals negative root 2? So he's like, yeah, good call. It has 2 solutions, but it says like, however, we're dealing with a physical problem where x is a distance. This is exactly what I was talking about. I'm a little spooked out. I gotta be honest with you guys.